Welcome to the lecture on turbulent flow calculations. So, in this lecture we are going to have some background about these stress terms and how they are modeled and what are those terminologies which are required to be known when we deal with the solution of the turbulence models. Also we will have some introduction about the turbulence models. So, what we have seen that in our earlier lectures in the past lecture even that you have the eddies because of the fluctuating component. So, you will have so because of the turbulence you will have the eddies of different length scale. You will have larger eddies, you may have these smaller eddies. So, they will have the different length scale and time scales also for their interaction. So, because they interact in a very complex manner and that needs to be modeled when we need to see the turbulence flow modeling. So, and you have the numerical methods basically which are available to capture this to predict or to study these turbulence. So, the methods which are used for studying this turbulence are broadly categorized or broadly divided in three categories. So, one is the turbulence models for the Reynolds equations. So, as we have seen that we focus on the mean flow and also the effect of turbulence on the mean flow properties. So, in that you are getting one extra term. So, and in this case what we do is that these extra terms which appear, which we have seen in the earlier lecture. So, they need to be modeled and they will be modeled with the classical turbulence model and basically one of that is the K epsilon turbulence model that is used, and also there is one model that is Reynolds Stress model. So, these models basically so they will be using they will be used for modeling these extra stress terms which are generated, that is Reynolds stresses, and for them the computational time or the resource which is required will be normally reasonably. So, and in most of the cases it has been seen that it predicts somewhat fine. So, so this approach is mostly used in most of the engineering flows. Next, the second category of the second approach is the large eddy simulation. So, now this large eddy simulation. So, it is the intermediate form of the turbulence calculation. So, here you will have to have the calculation which will be tracking the behavior of the larger eddies. So, you will have in the domain you will have the larger eddies as well as the smaller eddies. So, you will be doing that simulation based on or calculation based on the larger eddies, and the smaller eddies will be filtered. So, you will have the subgrid scale modeling for that. So, what we do is we will be tracking the behavior of larger eddies. So, what happens that you will have the space filtering of these unsteady Navier-Stokes equations and prior to that computation you will be doing these space filtration. You will be seeing the large eddies and the smaller eddies, and the larger eddies will be passed and the lower smaller eddies will be rejected, and then further these smaller eddies are also included using these subgrid scale modeling. So, So, what happens that in this case the computational resource if you talk about the resources or volume of calculation, it is more than these what we do using these turbulence models like K epsilon or so. So, this is the second category, and then normally recently we also do the direct numerical simulation, that is also known as DNS. So, they will be computing the mean flow as well as all the turbulent fluctuation components. So, this in that you have the unsteady Navier-Stokes equations, and they will be solved in that spatial grids. So, you will have the finer grids to account for the fluctuations, and the time scales are also taken, so that they can be even smaller time length scales. Time scales are also taken into account. So, that way you will have it will be taking large amount of time, but then they will be giving the most accurate results, but it will be taking basically very large time. So, computationally it is very costly. So, normally it is used for the industrial flow type of computations. Now, what we do is when we talk about the Reynolds averaged Navier-Stokes equations and about the classical turbulence models. So, in that what we have seen that normally we have the terms, these stress terms, and also stress terms like minus of rho of u prime v prime, of minus of rho of u prime w prime, and minus of rho of u prime square, that is averaged part. So, these are the stress terms which needs to be taken into, or if you have the scalar property also. So, u prime phi prime, so average part. So, these these parts needs to be modeled, and you have the also averaged Navier-Stokes equations. For that you have the turbulence models, and you have the turbulence models which we use normally is mixing length model as well as the K epsilon turbulence model, where you have the two equation model, you have one equation model, you have two equation model. So, these based on the additional number of transport equations which you need to solve for modeling these stress terms. So, based on that you have the different types of models which are used. I mean, they are known as the turbulence models. So, what happens that if you talk about the depending upon the number of transport equations which needs to be solved, and that way you have those equations solved. So, you have if you take the number of extra transport equation which needs to be solved, and the name of the model will be. So, suppose when you have a classical model, that is mixing length model, and that has nothing, you have an expression. So, that in that you get the expression for the eddy diffusivity. So, that we will see that what is that eddy diffusivity. So, and that is in terms of the mixing length. So, you will that length will be a function of the characteristic length of the flow domain. So, you will have that is 0 equation. So, since there is no extra equation needs to be solved. So, that is for the mixing length model. Similarly, you have one equation, one extra equation needs to be solved, and that is the Spalart-Elmaras model. So, in that you have one extra equation, transport equation needs to be solved for modeling these for taking into account these extra stress terms. Similarly, you have two extra equations needs to be solved for in certain cases, and that is for K and epsilon and that is developed by Spalding. So, you have that model known as K epsilon model. So, you have turbulent kinetic energy and you have the dissipation of kinetic energy equation. So, you have these two terms and you have these two terms, they are solved, and using the value of K and epsilon you get the value of those stress values. So, using the using the other parameters like nu t or so. So, that we will see. Similarly, you have the K omega model. So, that is also one where you have the two equations, one is K for K and another is for omega. Similarly, you have the algebraic stress model. So, in these models you solve two extra equations, and then from there you try to find the value of these additional stresses which we need to compute when we are solving the turbulence equations. Similarly, you will have 7 equations when you are using the Reynolds stress model. So, as you see that normally in the commercial CFD softwares you will have the provision of all these models, and you can use take into account any of the model and you can solve the problems. We will have some understanding about these models and what they are, especially about the main models which are used, and we will try to see that how they are used for the computation of these stresses, turbulent shear stresses, for modeling of that. So, coming to the concept of eddy viscosity and the eddy diffusivity. So, as we know that you have the eddying motion in the turbulence. So, you will have the stresses which are appearing on the right hand side, and as we see that you have the Newton's law of viscosity, where we say that you will have the stresses. So, that in that stress you take as proportional to the rate of the deformation of fluid element. So, that is what is being told by the Newton's law of viscosity. So that for incompressible fluid what we write is tau ij, that we write as mu of Sij. So, that is the Newton's law of viscosity, and in that we talk about these viscous stresses, and it is nothing but mu of dou ui by dou xj plus dou uj by dou xi. So, in this if I or j will be 1, in that case you take it as x, and if it is 2 then you can take it as the y, or if you take the j equal to 3, in that case it will be for the third direction, that is z direction. So, if you talk about tau 1 2, so it will be tau xy. So, it will be mu of dou u by dou y plus dou v by dou x. So, this is what normally we have understood. Now, when we talk about the turbulence, so in the turbulence you will have the decay of the turbulence also. So, so what is found that the turbulence decays unless there is shear. In isothermal incompressible flows. So, if there is no shear, then it will be decaying. So, that is there. Now, also it is found that the turbulent stresses are increasing as the mean rate of deformation increases. So, these turbulent stresses are found to increase as mean rate of deformation increases. So, if the mean rate of deformation will be increasing, in that case the turbulence is stresses are found to increase. So, based on that, these two findings, what Bosnisk has proposed, he proposed in 1877. So, the Bosnisk is proposing that these Reynolds stresses might be proportional to the mean rates of deformation. So, that way, based on these two findings, it can be said that the Reynolds stress might be proportional to the mean rate of deformation. So, it will be tau ij, that is mean Reynolds stress will be u I prime u j prime and average part. So, that will be this is your mean rates of deformation. So, this has been written as the equation mu t into dou u I by dou x j plus dou u j by dou x I minus of 2 by 3 rho k delta I j. This is delta I j is the Kronecker delta, and when I will be equal to j. So, that this term will be vanishing, delta I j vanishes in those cases. So, in that case this is expressed. So, when you will have this tau I j. So, now in this case the k, it is the turbulent kinetic energy, and it will be half of u prime. So, in this case k will be half of u prime square plus v prime square plus w prime square. So, this is basically turbulent kinetic energy per unit mass. Now, what you see in this case, this mu t, this is the turbulent viscosity or the eddy viscosity. This is known as the turbulent viscosity or eddy viscosity, and this is based on that you will have the term nu t. Nu t will be nothing but mu t by rho. So, that will be kinematic viscosity, kinematic turbulent viscosity or turbulent viscosity. Now, Kronecker delta I j, it will be 1 if I equal to j, and it will be 0 if I is not equal to j. So, it is basically in a matrix wherever I equal to j along the diagonal, it will have one part, and otherwise it will have the 0 part. So, that way you will have so it will be giving the correct result for the normal Reynolds stresses, where I will be equal to j. So, for the tau xx, that is minus of rho of u prime square, average of the term. So, and similarly you will have the tau yy or tau zz. So, you will have those terms coming into. Now, if you try to have the scalar part, if you have the if you take the turbulent transport of something like heat, mass or other scalar properties. So, in that case, so what we take is we are taking this term, and this is tau t. So, minus of rho of u I prime and phi prime. So, it is average value, it will be equal to tau t and dou of phi, that is mean value, by dou of x I. So, basically this term is it is known as the turbulent or eddy diffusivity. So, it is it's analogous to this term mu t. So, what happens that for other scalar quantity we use this tau t, and what we do, we have the Reynolds analogy. So, what we do is that we introduce a number, that is your Smith number. So, that is a turbulent Prandtl or the Smith number. So, that is defined as sigma t. So, we defined this sigma t, that is turbulent Prandtl or Smith number. So, that will be basically the turbulent viscosity divided by the diffusivity term. So, many a times we take its value as a constant, and normally we take it as unity in most of the cases, and in most of the CFD solvers they use this turbulent Prandtl number, turbulent this Prandtl or Smith number, that is taken as the value of unity. Now, coming to the different turbulence. So, as we see, we have so this is about the eddy viscosity part. Now, we come to the different turbulence models. As we have discussed that we have different turbulence models which are used are the mixing length model, where we describe the stress by means of simple algebraic formula for mu t, that is and it will be as a function of the position. So, we will have some value of position, that is Lm. So, mixing length is taken. So, in that term we are expressing this mu t value. So, that is why it is known as the mixing length model. Then you will have the K epsilon model, where you have two equations for K and epsilon, and based on that we find these mu t. Then you will have other equations like Reynolds Stress equation models, advanced turbulence models will be there, and also you will have the Reynolds turbulence models. So, this we will see. Now, if we talk about the mixing length model, so in this lecture we are going to have some idea about the mixing length model, how these mixing length model works, and how we are using it for the prediction of these stress component, turbulent stress components. So, this model will be attempts to describe the stresses by means of simple algebraic formula for mu t as a function of the position, and in this the assumption is that the turbulent viscosity mu t is isotropic, and it can be used to predict the turbulent transport of scalar quantities. So, what happens in this case, the turbulent stress this is turbulent Reynolds stress. What we do is we describe it in the form of this Lm square, rho Lm square, dou u by dou y and dou u by dou y here. So, basically what we see it is expressed in terms of this Lm, and then that is why we call it as a mixing length. Now, its value also varies. So, I mean there are certainly certain derivations for that. So, what is done is normally what we see that nu t, now in this you can write as the velocity scale and the length scale. So, because nu t has the unit of meter square per second. So, this is meter per second and meter. So, it will be meter square per second. So, if the one velocity scale and one length scale, that describes the effect of turbulence. So, in that case the dimensional analysis will yield to this equation, nu t will be C times V L. Now, this C is basically a dimensionless constant of proportionality. Because the nu t has the unit of meter square per second. Now, so we can write the mu t as C of rho V L. So, V is the velocity scale and L is the length scale. Now, most of the kinetic energy basically is contained in the largest eddies, and the turbulent length scale L, it is basically the the characteristic of these eddies, because they are containing most of the turbulent energies. So, and they are basically interacting with the mean flow. So, if you talk about the, so what you can say is there will be a strong connection between the mean flow and the behavior of these larger eddies, and we can also think of attempting this link to the velocity scale of the eddies with the mean flow properties. So, what is seen is that you can have the velocity scale as C of L times dou u by dou y. So, if you take the dimensionally, this will be dimensionally correct, because if the eddy scale is eddy scale length is L, in that case if you correlate it with the velocity gradient. So, so in that case and because the turbulent stresses, they are proportional to the they have also the relationship with the velocity gradient. So, you can have the velocity gradient that can be expressed in terms of C L dou u by dou y. So, basically if you use them, you can further write nu t as the Lm square and dou u by dou y. So, if you take all these terms together and you have the constant, so you can have the dou u by dou y. So, this is basically known as the Prandtl's mixing length model. So, this Lm which is coming, this is because of this term, this is known as mixing length. So, that is known as the mixing length model. And if the dou u by dou y is basically the only significant mean velocity gradient, so you can have the tau x y or tau y x, which we write as minus of rho of u prime v prime. So, it will be written as rho of Lm square and dou u by dou y. So, it will be nu t into dou u by dou y in fact. So, you can mu t into dou u, mu t will be rho into nu t. So, it will be this term, and then you will have the dou u by dou y. This dou u by dou y has been kept in mod because the velocity has to have the positive value. So, that is why it has been taken as the mod value. So, that way from this you try to have the modeling of or prediction of these stresses using these mixing length. So, basically what has happened that if it has been found these for different types of flow, you take these mixing length as different value, like for mixing layer you take these mixing length. So, this mixing length Lm, it will be 0.07 L, and L is the layer width. Similarly, if you have a jet, so in the case of jet you will have 0.09 L, where the L is the jet half width. So, for different types of flows, so you have wake. So, for wake, suppose wake type of flow, you will have 0.16 L, and this is again wake half width. So, for different type of flows, you have different values of these mixing length which is taken, and similarly for the boundary layer or even for the pipes and channels, you have one expression, that is L with respect to y, it will be varying. So, it will have a functional value, and you will have the L will be the pipe radius or the half of the channel width. So, those things are taken. So, you can have these values from the standard textbooks, and that can be used. So, they are used basically in the turbulence models when you are trying to have the prediction of these turbulent stresses using these. So, its use will be there in the Tundis flow basically when we do the Tundis modeling. In that case, when we have to predict the quantities, in that case which kind of model to be selected. So, being the simple model, it takes minimum time to solve. So, you can start with this model and then go to other models and see how they are predicting your different output parameters. So, this is about that. We will talk about more of the turbulence models which are used in commercial solvers or so. So, that will be in the next classes. Thank you very much.